All right, here's a good question for you, Fred. Folks at home too, push pause, make sure you give yourself a chance. What do you think, Fred? What's the answer?
Which of the following would not be expected to produce Cl minus when dissolved? I think they all would. Let's see. Yeah, I think that they pretty much all would.
How do you know that, Fred?
Because I was working on some dissociations. So, for example, sodium chloride.
Yeah, what would be the ions? When we see sodium chloride like that and a Cl aqueous, what is it that we should be thinking of?
A sodium ion.
Very good. A sodium ion, that means a +1 charge.
Oh, right. And a Cl minus.
Very good. That's right. So when we see this, we really are thinking of this. And so we can see that, yeah, if somebody says they have sodium chloride aqueous, we know that they have chloride ions floating around in solution. Very good. And that's the way it is for all these other ones?
Well, I guess not, because you're not saying good job. So let me look some more. Can you bring up your periodic table?
Sure. What are you interested in?
Well, I'm wondering if PCl3, P is not a metal. So this is not an ionic compound. So it's not going to create ions when it's placed in water.
Very good. That's it. That was the thing we were looking for. So PCl3, not an ionic compound, not going to result in chloride ions when placed in water. Very good. Okay, next. How many ions form on the dissociation of this compound? What's the name of this compound?
Sodium phosphate.
Very good. Sodium phosphate. And when I ask you folks at home, or when I ask Fred, what's the name of this compound, make sure you can tell me the name of that compound, okay? How many ions, Fred?
Just two, sodium ions and phosphate ions.
Did it ask what kind of compounds, Fred? Or kinds of ions?
What do you mean?
Well, you said that it's creating two ions, but you meant two kinds of ions, right? Because how many sodium ions would I get?
Oh, okay. I see what they're asking. They're saying 3 sodiums, and I guess you'd have one phosphate, so you'd have 4. A total of 4 ions.
Very good. That's what they're asking here. Not the different kinds, but how many of ions altogether, because that is important. It alters the amount of conductivity that a solution has. So if a lot of ions are released, then the solution has more conductivity than if fewer ions are released. So how about this one here? Folks at home, take your chance to answer the question too.
I'd say 5. 2 aluminum and 3 sulfate.
Very good. 5. Fabulous job. Okay, so when we get a chemical equation that has the combination of 2 ionic compounds that are aqueous, right? Let's think about what this actually means. If I have 2 ionic compounds that are aqueous, then that means I have a container of water, and this one has silver ions and nitrate ions, right? That's what silver nitrate aqueous means. And I'm combining it with another container over here that has what?
Potassium ions and chloride ions.
Very good, because it's potassium chloride. All right. Now, when I combine those together into a larger beaker, right, then my products are silver chloride and potassium nitrate, they say. And notice how what's happened here is you've just had the silver ion, which was the cation, trade places with the potassium ion. All right, silver went with chlorine, the chloride ion, and the potassium went with the nitrate ion. Very good. So when you have, and let's look at our solubility rules really quick. Is silver nitrate and potassium chloride, are they soluble? Let me see if I can find it.
You don't have to find it. I know. I looked at it.
Oh, you looked?
Yeah, all nitrates are soluble.
Very good. Why don't I bring up those rules, though, because I want to make sure that everybody knows where we're getting this, right? On the back of our periodic table, right next to our polyatomic ion chart, are these rules, right? And here you're saying that all nitrates are soluble. That's rule 2. And what's the other rule?
Well, chlorides are generally soluble as well. However, like you see, after the reaction's done, the chloride goes with the silver. So, and silver chloride is an exception. See Rule 3?
Yeah, rule 3. All chlorides are soluble except when combined with silver ion, lead ion, or mercury ion. Okay, good. So we got this chemical reaction here. And now we want to make sure as chemists, budding chemists, we see that what this really means is these ions in solution combining together this way and leaving behind these other ions, right? So this is what this can be translated to. And we call this the Ionic equation. And it's critical that we can learn to write the Ionic equation so that we can recognize the actual species that are performing the chemistry. Because as you see here, looking at the species on the left to those on the right, some things haven't changed, right? What two chemicals haven't changed?
The potassium ion and the nitrate ion are exactly the same.
That's right, they're exactly the same. So that means that those ions are what we call spectator ions, and we can drop them out in the Ionic equation, or the net Ionic equation, okay? So the net Ionic equation then shows only the chemistry that's occurring between the species that is occurring between, right? So we have silver ion and chloride ion coming together to form silver chloride, okay? Very good. So we identify our strong electrolytes, and in a chemical equation like this, generally the strong electrolytes will say aqueous, but we could always bring out our what?
The solubility rules.
That's right. You can always bring out your solubility rules to identify those strong electrolytes. Anything that's a strong electrolyte will be broken up in the Ionic equation, right? Identify the products. In these kind of reactions, oftentimes one of the products is a solid, right? We call that a precipitate. One of your compounds is a precipitate, and this then becomes what we call a precipitate reaction. Okay? And then you can even further boil it down to the net Ionic equation. So here's some more examples of these Ionic reactions, right? Here I have lead nitrate dissolved in water, colorless. Here's potassium iodide dissolved in water. If I combine these two flasks together, then what I get is a precipitate, a yellow powder, which is in the water. It's not dissolved in the water anymore. It comes crashing out. But that's lead iodide, right? So what's again happened is our ions are separated here, and we bring them together and we form a precipitate. Here's a video of another kind of chemical reaction. Two ionic compounds dissolved in solution, and we mix them together and one of them precipitates out. This is again a powder in that water. If you just let it settle, it will, over a long period of time, just collect on the bottom and leave behind the spectator ions in the solution up above. Okay? Very good. So, do you think you can write the Ionic equation for these reactions?
I don't know what they're talking about.
Well, the Ionic equation is essentially looking at our compounds that are aqueous, or that will be strong electrolytes, and our periodic table, or on the back of the periodic table, the solubility rules can help us with that. And then we write the compounds dissociated, and we get rid of, well, that's just the Ionic equation. That's where we stop. To get the net Ionic equation, we would get rid of the spectator ions. So if we're going to write barium chloride broken up into its ions, what would we get if we broke barium chloride up into its ions?
Oh, you get a barium ion plus 2 charge.
Very good.
And you get 2 chloride ions.
The -1 charge.
Oh yeah, with the -1 charge. And then you get a lead. What's the charge on that lead?
I don't know. How do we determine that?
We need our, I need to know the charge on the nitrate. So let me look at my table here. Oh, nitrate's a -1. So There's 2. So that's lead with a +2 charge.
Very good. So the name of that compound is lead 2 nitrate, right?
Yeah. Okay, so now I get 2 nitrate ions with the -1 charge.
That's right. Very good. So that is our reactant side of our ionic equation. Good job. And then the product side, we don't write the solid compound. We don't dissociate that. It is not a strong electrolyte. It's a non-electrolyte, right? Based on our solubility rules and based on the fact that they provided it as a solid in this reaction. And then our barium ion with its nitrate ion are again going to be broken up. And we can identify spectator ions, right? Very good. So why don't you take a stab at that last one there, and we'll show the folks at home, okay?
Okay.
Did you get to take a chance at it, folks at home? Push pause if you didn't. I'm going to show you the answer now. Okay, so again, we got the right number of ions of sodium, carbonate, calcium, and chloride. The insoluble salt is displayed as a solid, and then the rest are just ions again. Okay, fabulous job. Wonderful work today, Fred.
Well, thank you.